Okay, so you might be wondering, before we had F equals mg for the force of gravity, but now we have Newton's law of universal gravitation, that F equals g m1 m2 over r12 squared. And you might wonder, what is the relationship between those? Like, those are wildly different expressions, and yet they're both supposedly representing the force of gravity. Well, it can be instructive to try this for simple cases near the surface of the Earth. Okay, so let's say that we have an object with mass MO for object that is being attracted to the Earth. Okay, well, the force that we expect in that case is g times mass of the object times mass of the Earth over the distance between the object and the Earth squared. Now that's a little bit dicey actually, because if the object is sitting on the Earth's surface, isn't the distance between the object and the Earth 0? Well, that's true, but we know from our everyday lives that the force of gravity doesn't change dramatically if you put an object near the surface of the Earth. So the only reasonable interpretation for this is that this should be the distance from the center of the Earth. Okay, so we use the radius of the Earth as the distance between the object and the center of the Earth. In a future video, we're going to explore whether that actually makes sense or not. But for now, we'll just use that and see what happens. Okay, so the radius of the Earth is something you can look up. That is going to be 6.4 times 10 to the 6 meters. The mass of the Earth, you can also Google. That comes out to about 6.0 times 10 to the 24 kilograms. Although how we know that is maybe something you should think about a little bit. And so now we can actually plug stuff in. Okay, so if I do this, then I get F equals G, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of the Earth, which is 6.0 times 10 to the 24 kilograms, over that distance squared, so 6.4 times 10 to the 6 meters squared, times the mass of the object, which I'll just leave there. And if you go through and calculate that, you plug it into your calculator, then what you get is 9.8 meters per second squared times the mass of the object, which is the same thing that we had before for m times g. So it just happens if you take g times the mass of the Earth divided by the radius of the Earth squared, you get the acceleration due to gravity. That's not really a coincidence, of course. It has to work out that way if Newton's law of universal gravitation is true. Notice that if you changed your elevation by, say, several hundred meters, there would not be a very big difference in g. You'd get a slight variation, but because the radius of the Earth is already so large, those small differences are not very noticeable. So really, what is the relationship between these two forces? Well, the force of gravity as a function of distance is going to look like this. It's going to have a 1 over r squared relationship. But at the radius of the Earth, it's going to have some value. Okay, and it's just that we live in space that's so close to the surface of the Earth that we can just use that value and pretend it's constant, because we don't live in a very big range here, and so the force doesn't seem to change very much. But if you consider what happens to the force on that object as it gets really far away from the Earth, then you'll notice that the force gets weaker and weaker. Okay, so the force is noticeably smaller at the space shuttle. It's not very small yet, but it is, noticeable. The force on the moon is dramatically smaller than what you would have expected based on F equals mg.